Today I'd like to talk a little bit about what are the implications of this hypothesis a little bit closer to the sun. What about when we're talking about very close in, where it looks like from the graph these gravitational forces can vary widely. So I'm going to discuss a little bit about that now. What I am talking about is this region of the graph here. When I was creating this equation, which as I said is just a very rough data fitting guess just to get started with, I was really more concerned with behavior out near the planets. And so I wasn't as concerned about this region in here. And what's going on in here, I don't really have any data for. And so I'm not sure if this equation is approximately reasonable or it's not reasonable. But nevertheless, I would like to take some, do a little speculating on what this general idea might possibly mean when we're talking about things like neutron stars, when we're talking about things like planet stability, or when we're talking about things like black holes. First, I'm going to talk about neutron stars. Before we get into that, we kind of have to understand a little bit about the atom. So traditionally we show the nucleus of the atom here, and we show it as electrons orbiting the atom. But in order to understand about neutron stars, we have to understand that these sizes are not proportional, they're not realistic. In real life, let's suppose this nucleus was the size of a ping pong ball. So where would these electrons be orbiting? First of all, they'd be like microscopic, so they'd be tremendously smaller than the nucleus. That's the first thing. The second thing is this electron would be orbiting about a half a mile away from the nucleus if we drew it to scale. And so the point I'm trying to make is that an atom is almost entirely empty space. So I was trying to explain about the proportional size in an atom because I'm trying to get across the idea of just the fact that we are like almost entirely empty space. The only reason that something feels solid to us is the electromagnetic repulsive forces between electrons don't allow atoms to press past each other. And so that's why things feel solid to us. But in reality, if you understand the way atoms are constructed, we are almost entirely empty space. Now, when we talk about something like a neutron star, what has happened is, in that case, once the star sort of burns out, the electromagnetic forces are no longer strong enough to resist the pull of gravity, and all of the atoms comprising the neutron star kind of get crunched together, so the neutron star becomes just a gigantic nucleus. Okay, now I don't know exactly, but I think, for example, if you were to take a sample of a piece of the neutron star, if you had a piece something like the size of a basketball, it would have a mass equal to the Earth. And the only thing is, with a neutron star, its gravity becomes so dense and so strong that it almost has the ability to trap light. It can bend light, the path of light, it can be bent so much that if you're looking at a neutron star, you could probably see the backside of it, because any light that escapes its backside might be bent enough, so that you could see it. So it bends light tremendously, but it doesn't trap light. Light can still escape from a neutron star, but that's not the case if we're talking about a black hole. So here we have a diagram of a black hole, and there's something called the Schwarzschild radius. And all that means is that at the Schwarzschild radius, the gravitational strength of a black hole is so strong that light cannot escape. And according to current theory, the space around a black hole is pulled and stretched like this, that this means that nothing can escape the black hole. Now, at the heart of a black hole is presumed, according to current theory, to be a singularity, and that just means a point that is infinitely dense, much more dense than a neutron star. So the idea is that if a star, when it's getting near the end of its life, if its mass is sufficiently great, it will become a black hole. If it's not quite got enough mass for that, it will become a neutron star. So my point in bringing all this up is that the only reason that current theory posits a singularity at the heart of a black hole is that according to current theory, GR, space can stretch or warp or deform. And so you can have a point on the inside of a black hole, the singularity, where matter can be infinitely dense. And this is why light cannot escape. According to current theory, a neutron star, its gravity would not be strong enough to trap light. And so the thing that I'm about to say that would be tremendously controversial according to current theory is that if what I'm saying is correct, and that gravity varies in a wave function like this, such as I've described in my hypothesis, then that means that at certain sizes, a neutron star's gravity at certain distance from it, because gravity varies as a wave function in the way I've described, there may be a peak of the wave function somewhere near the surface of a neutron star, such that its gravity is orders of magnitude larger than current theory allows. And what this might mean is that at the heart of any black hole we find is not going to be a singularity. Instead, what's going to be at the heart of any black hole is a neutron star.